His undergraduate work at UNAM's engineering faculty is early neural networks and robotics led to being awarded Mexico's National Youth Prize. His PhD at Oxford pioneered visual wearable computing, including one of the first demonstrations of visual 6D SLAM applied to augmented reality and robotics. He has co-authored over 100 papers at top venues in computer vision, mobile systems, and robotics. His robust SLAM work was commercially released in the world's first product with 6D visual mapping and licensed by Samsung for their flagship humanoid robot project. His research has received Best Paper Award nominations at IEEE, ICRA, and 6G, and has been featured in The Economist, Discovery Channel, and El País. He founded the University of Bristol Robotics Research Group and served as inaugural deputy director of the Bristol's Robotic Laboratory, Europe's most comprehensive robotics facility. He has also served as general chair twice for IEEE ISMAR, the most important academic gathering in mixed and augmented reality, and as general co-chair for the British Machine Vision Conference. Since 2017, he has led CV and AI teams launching first-to-world products including virtual tourism, augmented reality devices, and Amazon's first AI-generated advertising. He would love to give his talk in Spanish to prove he is still, I don't know how to translate this.
Chilango.
He's still Chilango, but he is happy to disagree and commit. Please join me in welcoming Professor Walterio Mayol Cuevas.
Thank you. Thank you, Humberto. Thank you so much. And for me, it's an absolute honor to be here in Mexican Conference Panel Recognition. I always followed it, and I have helped reviewing, and I am always excited about what happened here. But let me start by dedicating this talk to those of you that do research or teach in Mexico, because you're inspiring the next generation, just as I was at some point. So thank you very much for that. And as Humberto was saying, so I have a dual affiliation, but everything that I'm going to say here is with my academic hat, and all my opinions and points of view are my own. Okay, so safe disclosure. Okay, and every time I give a talk in Mexico, I actually start showing this slide, because this celebrates Arturo Rosenbluth Stearns, who is Mexican. And he's one of the founding fathers of cybernetics, which is an early take on AI. And today is even more special for me because Rosenbluth actually was born here in Chihuahua, in Ciudad Vicente Guerrero. I checked, and it's 5 hours drive from here. Chihuahua is the largest state in Mexico, of course. So, but he's from Chihuahua, and Arturo Rosenbluth certainly started together with others in the 1940s, this very interesting new scientific direction on how to understand biological systems and artificial systems. And this is where cybernetics actually really started about. So this is super exciting. And also in the 1940s, there was a lot of activity. Another example will be Vannevar Bush, who coined a concept that was called memics. Memics was a concept. He didn't actually implement it, but it was like a visualization of the future, where he imagined a future device where you will be able to store all the information of the world, all the things that you experienced, and eventually retrieve it and consult and check what was going on. He was using technology to visualize the concept that was available in the 1940s, so microfilms and electromechanical systems. But does this concept sound familiar to you today, right? So early 1940s activity. He also envisioned that people will be wearing cameras and capturing what they were doing. And all this data and information was going to be fed to this desk. It was also visualized as a desk, an intelligent desk, where you will be able to actually retrieve and consult all the information that you ever wanted. So this is the 1940s. Okay, so let's just recognize that artificial intelligence and this type of cybernetic type of systems have a long story with us. So AI, even from the beginning, the other point I want to make, when we think about mimics and you wearing cameras and sensors, AI had, even since inception, a mirror twin. In English, the acronym will be intelligence augmentation. So it's not just artificial intelligence, but how do you use this type of devices to intelligently augment your capabilities, right? So this is, again, very early inception of systems. There was already a plan to try to use these devices to actually help people to be better. So in this talk, I'm going to have two parts. The first part, I'm going to share with you some recent research academic work that I've been doing with colleagues and students at the university. And then I'm going to also have a personal commentary about some experiences in industry, specifically in US corporate industry and research. Let's also stick with looking at the past to understand the future. So if we actually think about how augmented reality systems and extended reality systems looked around 30 years ago, they will look like this. This is a system called Karma by one of my colleagues in augmented reality, Steve Feiner and his students. And it was one of those early visualization of how augmented reality was meant to be working and helping us, okay? And so what you have here is a person that is interacting with a device, in this case, a printer. And what you see here in the circles, these triangles that you see here are positioning systems. They were using ultrasound to know where everything in space is. Where is the printer? Where is the cartridge? Where is the display? And if you know all this information, then you can do augmentation and you can show things that are like on the right? So you show how are you going to repair or operate that machine, okay? And since then, about 30 years ago, a lot of research was concentrated on trying to solve the problem of how to remove the markers. So instead of attaching things to objects, a lot of the research in this space, my own research included, this is what I did as part of my PhD back in 2003 with a colleague, Andrew Davison, who is now a professor in Imperial College. We demonstrated what many regard as one of the very first demonstrations of visual mapping with a single camera. So no markers in the environment, maybe just for initialization. And the idea was that you were going to wear this camera and the system starts initializing points. These squares that you see there are points that eventually are figured out where their 3D position is. And after you are able to know where you are relative to the environment, then you can remove the markers that we saw, and then you can start doing augmented reality, which is essentially what we did at some point. But despite all this work, despite 30 years or more of research in the space towards making these devices more suitable for live spaces, so you don't have to add markers or anything like that, where is our AR and AI assistant? So today, that device still does not exist. Something that I can just wear and suddenly makes me a superhuman. It doesn't exist yet, right? So these devices still lack a lot of things to actually succeed. I will be talking a lot about the history about this and so on. But one of the reasons why these devices are still not universally useful is because, as I mentioned, a lot of people, myself included, worked on trying to solve the spatial problem, maybe also the hardware problem, right? And the devices that I showed in the previous slide are actually amazing devices. But most people didn't look at this other side of the problem, what you're going to show. So how do you create the content that you're going to display on the head-mounted displays is something that was essentially ignored for quite a long time. With generative AI, there is more promise, but in our team in Bristol, we started working on how to actually create automatically information that you can then display later on. And this is one of those early devices. We call it Glacier. And essentially what it did, it essentially using Google Glass, one early wearable computer eyewear. The device was observing people, immediately detected when you were doing something interesting. So it had like an attention detector and started grabbing videos of what people is doing in those moments. And in this case, the person is setting up an oscilloscope. And so the device starts capturing a small video around those moments of interest. This is the view from the device. And eventually, you have a lot of videos that you have collected from lots of people that are doing the same task, right? So the idea here with this device is that after you collect these videos, you then surface to the person that doesn't know what to do in front of that machine, the steps, the small video guide that helps you to solve the problem. So imagine that you have YouTube immediately triggering how do you change the light bulb in your car, right? That type of experience is what we're interested in. But after you collect all this information, after you collect all this data, again, imagine YouTube, you go into YouTube and you end watching Ricky Martin or something totally unrelated to what you're looking for, because the content is not organized. So how do you organize that? So this is a problem that we started working on, which is how do we actually structure that data? And this is another work that we presented at CVPR, where we're interested in understanding the ranking of skill. So in this case, you see a video of someone doing a task initially better and someone doing it initially worse, right? And the idea is that the machine is able to understand, in this particular paper, moments when the action is happening with high skill and with low skill, okay? Because if you know which moments of the action are showing high skill and low skill, then you can start organizing the information, the video information, so that you surface what is actually interesting and relevant for that moment. And you show the best examples, okay? So this is some work that we did a few years ago. Today, in my team, we're interested in yet another problem that has also been ignored for a long time. So we talked about positioning, we talked about content authoring, but now, in my opinion, we need to start moving more into what is happening in the person. What is in the mind of the user? What is the skill that that person has? What is the frustration or not frustration that person is having, so that you actually understand when to intervene and how to intervene, okay? So with this piece of work, we started looking at recognizing struggle. And let me just play this video because I find it extremely fascinating. So it's a video from Warneken and Tomasello, who has studied this problem from the experimental psychology point of view. So. I think I was stopped. Thank you.
Oh.
What I find extremely fascinating about that is that this is an example of a pre-verbal kid. So this is a toddler, still don't speak, right? But they are still able to not only recognize the person is struggling, but they also offer help, right? To me, this is extremely, extremely exciting because it shows that even if you cannot even describe what is happening. You might not even know about rock climbing or how to operate a steam engine. You can still recognize if someone is struggling. Does that make sense? Yeah. And that means that there is a fundamental capability that we all have that appears strongly connected to how we learn and how do we organize information. So if machines are able to recognize struggle, then we can create much better artificial intelligence systems that can help us in the right moment. Now, struggle is not an error, and this is something we have battled with reviewers in many conferences and journals, because in the community of egocentric vision, there has been a lot of work about recognizing errors. And to recognize an error, you actually need to know what you are doing. And that's a very different thing. But because there is a lot of work around errors, it's important to explain that struggle is not an error, because you can perform a task without errors, but still struggle. Imagine that you're trying to make a cake in the kitchen, and you make the cake, you complete the cake, but you make a mess in the kitchen, right? You struggle all throughout. No error whatsoever, but you still struggle, right? So that is different from an error. Now, it's also possible to confidently appear that you're solving a task, making lots of errors. So errors and struggle are related, but they are not the same thing. And this is important distinction because we need these machines to be able to make that distinction. And what I find even more promising about struggle, as I mentioned, is that you don't need to know about the task in order to recognize a struggle. So it means that there is something universal that if machines are able to recognize, they will be far better than how they are today. Now, what are the types of struggle? So you can imagine that people is trying to repeat a task. There is some assembly errors, so aligned with errors as well. People may stop, throw their arms in the air because they don't know what to do. This will be examples of that. So if you look at these videos, this person is trying to assemble. This is from our data set from IJCB 2025. This person is trying to complete the task, but then suddenly stops, doesn't know what to do. This one is knowing what to do, so there is no hesitation. So if you actually look at these videos, this is even more obvious because this person is hesitating. Where does this piece go? It goes here, it goes there, then pauses, then it might correct, right? So these are telltale signs of the person struggling that you all can detect and recognize. So we started collecting these data sets, and we started to put some baseline detection on the struggle determination. And in the IJCB paper last year, we show that it's possible to recognize within these simplified cases, it's possible to recognize a struggle, especially if you train for the towers of Hanoi, you can recognize a struggle in the towers of Hanoi. So that's not very surprising, but still some signs in the right direction. We also tested different angles of the problem. So what happens if you train only with the early examples or the later examples? It appears that you really need to have diversity in the data set from both struggle examples and confident examples in order for systems to recognize. And this is a new data set that we are releasing with a paper in MCPR this year, where we're also now interested in the evolution of struggle. Because maybe you're struggling today because it's the first time you're doing the task, but by the fifth time you do the task, then you are no longer struggling, right? So in this new data set, we actually collect multiple attempts on how people evolve that struggle. And we use this information as well to train systems. In a way, this is a labeling-free example, because the early attempts, even if you don't label them, because labeling this type of data sets is actually very complex and laborious, it's very subjective as well. But if you use the evolution of struggle, you can have some sort of free labeling that the early examples will have more struggle and the later examples will have less struggle. So you have some sort of gradient that can help a model to actually be better at recognizing how this evolution of the struggle and the skill actually happens. So this new data set has another set of tasks. We have things like tying knots, origami, tangrams, shuffling cards. You will see people struggling to do all these things in the beginning. They might make a mess in there. And then for each one of these tasks, we also have multiple repetitions. So we have the same person doing the same task several times, and we collect all this data. And this will be yet one more visualization where it's the same person, but on the left is the first time they are doing this task. So you will see they are moving with less confidence. There are pauses, they're checking the instructions, hesitating what to do. On the right, the person is now more familiar with the task, far more quickly. They are able to recognize what they need to do next, and they know the steps. So we have run several models to try to baseline what happens when we train within specific tasks, within a combination of different levels of skill and struggle. And these models are able to do an okay task, but and this result is from yet another paper where we also do real-time detection. So because at the end of the day, if you have a smart device and a smart AI that is meant to help you in the right moment, you need to recognize the person struggling now. It doesn't help if you recognize the person was struggling. So we also develop some online systems, and we are able to detect. So if you see here, let me see if I can move this. So this is the ground truth for struggling. Our model is in green, detecting the moments where the struggle is, no, apologies. Our model is in blue, and green is the following of the ground truth. So in blue, you can see that the system is able to recognize online when the struggle is happening. So this is encouraging, but I will not imagine that this is anywhere near done, because even if some generalization can be demonstrated. So for example, if you train with tying knots and you want to recognize origami, you seem to get some 75% of the times that are correct. But there are other cases where we train with shuffling cards, and you then only recognize about 50% of the cases. So I think the generalization of skill is still one big challenge, but that connects with what I was arguing before. We really need to bring that universal ability of AI to recognize struggle, and we're still not there. But there are some encouraging signs, and we hope that the data sets that we are introducing are going to help the community to work more in this space. All right, so this is the first bit of research that I wanted to present to you, academic work. But continuing with the line of intelligent AI that we can interact with, there is another component. Coming back to the early illustrations, we have sensors like cameras. Cameras are fantastic from the point of view of capturing many aspects of information, color, textures, movement, and so on, time. But what type of camera should we use? The early concepts will use a standard. I think even Vannevar Bush was imagining that this was a film-based camera, so not even digital camera, because it didn't exist. It's a film-based camera you develop, you later ingest into the MEMX machine. Today, we have devices that have dozens of cameras, different types of cameras, right? But the question still remains, how do we actually should sense the world, especially the visual world? And this is the second piece of research that I wanted to talk to you about, that I have been developing for quite a number of years now, more than 15 years. And it's a collaboration between the University of Bristol and the University of Manchester. And this is around how to develop new types of information and computation that is no longer separated. So let's just think about how a computer vision system looks today. So today you can imagine you have a camera, and the camera sends a lot of images down a visual pipeline that eventually reaches something like a CPU. The CPU is unable to deal with all the data that is coming through, needs something like a GPU, and eventually all this connects to something that through more steps leads to action. So you connect that to a robot arm or something like that, right? So these type of visual pipelines were designed not for AI or for computer vision, not for robotics for sure. They were designed, these type of cameras were designed to capture images at a wedding. GPUs generated initially for gaming. So these components, they work, and they work fairly well today to some degree, but they still lack a lot of efficiency. And a lot of wastefulness is happening because of the way in which we are using this type of traditional pipelines in computer vision. So with these new type of devices that we call pixel processor arrays, that I will explain in a moment how they work, the hope and what we're seeing even today is that we can go immediately from capturing light to issuing commands. So instead of sending useless information down the visual pipeline, you're actually just sending the direction of the object, the identity of the object, or high-level information that is necessary and only sufficient for any of the tasks that you want to do, maybe directly connecting to motors, something that we have actually done already. The benefits of doing something like this, if we can redesign the visual pipeline, is that we will have lower energy consumption, lower latency, and much reduced systems complexity. So this might sound very advanced, but looking at how nature has also addressed this type of low energy, low latency, low system complexity, we should point to some research that actually there's a paper, a beautiful title that says, "What the Frog's Eye Tells the Frog's Brain." And this is by some very good, very renowned scientists in the neurophysiology literature. When they presented this paper, no one believed them. No one believed what I'm going to show you next, because it goes counter to this notion of cameras are for capturing images, the brain is for processing. This is a frog that my 7-year-old drew at the time. And this is the paper by Ledvin, Maturana, and McCulloch back in the 1950s. They observed that in the retina of the frog, there were what they described as a bug detectors. Okay? So what this means is that there were cells in the retina that triggered, not when they only recognized something that appeared to have the shape of a bug, but also behaved like a bug. Okay? Not just the shape, also there is some behavior recognition happening in the retina that tells the brain of the frog to obviously act. Okay? So this is an example of several that are out there of how the processing can happen at the moment you're actually capturing light. And therefore, I think we should start considering what I will call a visual computation continuum. So instead of imagining that cameras are just for sending information, brains are for processing, and they happen in different parts, you can imagine that now we can have computation along a much broader pipeline, a much larger broad region, where you can have the sensor on one side, you can have the back end, like the GPU, energy hungry, on the other end, And then you can have things that are near the sensor, near the back end. And then you can start thinking that different elements of visual computation could happen in different parts of this continuum. So event detection, which is very popular, another type of neuromorphic type of event, of element can happen near the sensor or actually on the sensor. On the other end, you can have things that require a lot more information, like mapping and long-term memory. And so you can start thinking about different things that you are interested in happening not just in one part or another. They can start to be distributed along the visual pipeline. And things like what we have done also before is that if you have something like a convolutional neural network, you can have some layers in the eye, some others close to the eye, some others much further back. And you can start to distribute that in a much better way. And of course, there might be many other things that today we're not considering that could be now deployed and efficiently implemented if we start removing that notion of the eye does one thing and the brain does another one. So this is what we call the pixel processor array. This architecture was developed by my colleague Piotr Dudek, who is a professor in Manchester University, and he has been developing these for more than 20 years. And the idea of the pixel processor arrays is that for every single pixel, you have a CPU next to it, right? So, and these CPUs are all connected in parallel. So you can have a massively parallel processor that is able to capture and process light at the same time you are capturing it. Okay, and we have applied this. This is some early example of us mounting this on a drone, where the PPA recognizes these squares and calculates the attitude of the drone and sends the commands to the drone in order to navigate through this. So all the key computation and sensing is happening on the actual sensor processor. We don't require anything else. We have also put convolutional networks
for conducting CNN inference
in there. We have also built mapping systems. This is actually the work of Hector Castillo from Mexico, who did his master's with me. And what he developed was this system where we can actually build a map. We can actually build a map of the environment by just moving the camera around. So he's moving around, the camera is capturing images, and on the PPA, on the actual device, we are storing this information and then eventually matching it with another image at another time. So the device itself is building a map, a visual map of the environment. It's not a 3D map, it's just a visual map, just a collection of images that you are going through. But what you see here on this button over here, it will appear again. This is just indicating where the system thinks it is based on a particle filter that we implemented inside the device. And we have tested this with a number of data sets and so on. It's actually very encouraging to see that on the eye itself, you can actually build maps and so on. But this is the latest work that we are presenting at ECCV 2026 this year, where we took one step further, where now we're building a 3D map in cooperation with the backend. So what we are able to do here is that in the traditional system, you might be able to run a camera 60 hertz, and because you have to send all the images back, you're sending, let's say, 500,000 bytes per frame, okay? And this goes into a backend, the computer with the GPU, and you're able to run SLAM at 60 hertz. If we actually split the computation between the camera and the backend, we're now able to do something like 2,000 frames per second by doing the tracking and the feature detection on the PPA and only sending about 200 bytes per frame, which contains the descriptors for the feature map, for the feature in the map that we want to build. And this is what is sent to the backend, which now is able to run faster because it's not doing anything else. So it runs faster the same machine. And interestingly, this backend can start sending information back to the eye, to the sensor processor, and the eye now becomes more efficient because of the information that is in the map that you're building. So there will be more details in the paper that we have. This is just a video where you can see the system running at 2000 frames per second in the front end and 200 hertz in the back end, where the system is just moving. And we're comparing this with the motion capture system in there. So let me click. Well, hopefully you got the idea. I'm struggling to. So this is another visualization of the system just tracking features, 2000 frames per second. So you can really move this very, very fast. The system has low latency, low energy consumption, about 5 watts in total, and so on. All right. So that's the end of part one, academic research. And what I wanted to do in this second part is to just talk about the last 20 minutes that I have. Is that true? I want to talk a little bit about some experiences that I have had working in industry, deploying computer vision and CV at scale. Again, this is a personal point of view and all that. And one thing that I've been extremely fortunate of is to have a very wide exposure to many different and diverse products that we have launched. So I worked on the very first virtual tourism plus shopping experience. This was released during the pandemic, so it was extremely successful. Back then, you were able to visit remote places, including many cities in Mexico. You were able to buy things, and the things would appear as part of your shopping in Amazon. So it was quite an experience, many other things that you were able to do there. I also was involved on leading computer vision for devices like this one. This is Amazon Glow, where the idea is that you have augmented reality with projection-based for a communication device that help kids connect with remote families. So many kids will have the grandma living in a different state or country. How do they connect? How do they interact? So we developed a lot of computer vision to supplement that interaction. It was extremely loved device. I also was involved in the early stages of the Amazon AR delivery glasses. I was involved on the computer vision side and sensor consideration and placements for helping Amazon delivery drivers to have a much more efficient job. You want to imagine how chaotic it is when an Amazon delivery driver or a delivery driver actually has to deliver your package. But with AR, you can actually bring some superhuman abilities that otherwise will be very difficult to achieve. And more recently, I've been leading the generative AI for Amazon advertising, and we have launched the very first one-click video ad generators that have been widely adopted by people. So I've been extremely fortunate to be exposed to a variety of products and problems. And here again, sharing just a token of experiences that I have encountered. And one thing that we all face in the scientific community and also in industry is that everyone thinks that they are right? And that is actually true in my experience. Everyone is right. What area you're going to work, what algorithms you're going to use, what products you're going to develop, that is when you have an opinion about when you're right. Everyone is right except for the timing. And what does that mean? It means that taking again the example of eyewear computing, the early notions of eyewear computing started very early. There are even literature pieces in the 1930s talking about smart glasses. But there have been several attempts, Sutherland's the Sword of Damocles work in the 60s, and even in popular culture like the Terminator vision, where the information is overlaid on your view. These things obviously have popularized and kind of prepared the environment for us to try to develop this type of devices. And so when we talk about opinions, you might have Alice and Bob, and they might have different opinions about what is going to work. So Alice may say, yes, eyewear computing is going to work. Bob is still skeptical and says, this is never going to work, right? Reasonable postures. Then suddenly, something like Google Glass that breaks in and is the first self-contained eyewear device, and Alice feels reivindicated because she was right? So she feels, I was right, and she tells Bob, I'm right, you're wrong, see how this is working, right? But then, of course, things happen, and some of these devices get canceled, and then Bob feels reivindicated, and Bob thinks, I told you, I'm right, so, right? And Alice didn't get it right that time. But then things keep evolving, more devices get launched, even something like one of the most successful one, the Meta Ray-Bans, are out there. And these devices are more along the lines of fashion, okay? And if you think that fashion is not something that humans are interested in, you will be very surprised, because if you actually look way back, 1.7 million years ago, Acheulean axis, have you ever seen these tools, early tools? Not the earliest hominid tools, but early tools, right? The reason why I'm showing this here is because there is a hypothesis that many of these tools were actually developed to impress the potential mate. Why? Because they have found thousands of tools that were never used, okay? And all together. So maybe ways to impress people is also part of our humanity. But anyway, these devices are developed. And Alice now starts thinking, well, this is not the vision that I wanted. So it starts to have some question marks around. And Bob kind of says, well, now this has sold millions of devices, so maybe this is going to work now, right? So these postures can change. And so going along the line of everyone is right, except for the timing, what is happening is that independent of your posture, what really is waiting on how right or how wrong you are is really about the timing and not about your posture. And this is important to recognize, because sometimes we get very obsessed about how do we support areas in science or product development, because we might not be right. It might just be that the timing is not right. And the timing is something that we actually don't fully control, because there are many things that play and come into context when you have to decide. So if timing is not in your side, what is in your side? What is in our side? So independently of the posture that you have, and I think this is a very important thing that I have observed, that is the only thing that we really have control about, is your passion. If you're actually passionate about what you're doing, and you have a passion about the vision of what you think should work, and you genuinely are passionate about that, and that's not simple. You're obsessing about something, and you genuinely obsess in science or industry about something, then eventually the timing is more likely to align with you, but only if you have that passion. And I have seen this in countless examples in industry and science. So when you think you're right, I think this is the other side, don't be overly flamboyant, because you might actually be wrong next month, right? When things happen. So be respectful about others' opinions. Time may not be on your side. Recognize that you might be right only temporarily and not universally. The other lesson I have seen, and there have been also very interesting research around this, is the importance of diversity in teams. There have been science works like Uzi et al., and there is another recent work showing the impact of scientific work along a long trajectory of people. Diversity, when you're assembling research or a team, appears to benefit your chances of having impact in science. So creating teams that have a wide variety of expertises. In this particular example, they pitch for have a core team that is very specialized in something, and then a few other people that have specialization in slightly different fields or totally different fields. So a core specialization and then some diversity there. And in industry, what I have seen at Amazon, there's actually a say attributed to Jeff Bezos that no team should be bigger than one that can be fed by 2 pizzas. So there is a 2 pizza team type of way to allocate resources. And what this means is that you have to have a self-contained team that is really small, that has a lot of ownership. You are in charge. You as a small team, you have to charge, just like a startup or a small scientific team that is trying to make a breakthrough. You are in charge. You have the ownership, and you have to deliver, and you have to bring all that expertise that is in there together. In the 2 pizza teams that I've been at Amazon, they are all self-contained. So you have scientists, you have product people, business, engineers, UX. It's a small team, and they deliver a product that reaches millions of people, innovates, and so on. So it's a very interesting lesson. So what this seems to be saying is that there is an importance of diversity. So if you're early or later in your career, you might start early by focusing and specializing on something, and eventually going into diversification. That's one path. I will not be pretentious and say that this is prescriptive. I think the importance is that even if you start the other way around and early in your career you diversify and you later specialize, that's also okay, because that brings that diversity. Your journey is very likely to be a combination of all these different paths. And one of the promises that today we can hope for that AI is going to help us is that potentially AI-assisted science will help us to be both very specialized and very diverse. So the scientists of today very likely can benefit much more from AI if we can actually combine it to bridge this gap of not having to first do one or the other, right? And I think this is an important thing. And essentially, I'm closing the presentation here, talking about AI in general. We had to talk about AI in general for sure. And just also looking a little bit at the past. So about 4,000 years ago, if you wanted to write a message or read a message, you had to go and queue and pay the scribe, okay? And only those that knew how to read and write were able to have the knowledge. In fact, there have been tablets that at the bottom of the tablet, there is a legend that says, only, essentially paraphrasing, only show this to those who know, and those that don't know should not see this. So that you keep the knowledge within the scribes. That, of course, is bad. Scribes were mostly male. They created something hyper complicated like cuneiform scripture that only they could read and write. And locking that knowledge, of course, was absolutely detrimental to humanity. Imagine that that didn't happen. And AI existed back in Mesopotamia. Humanity will not have died, for sure. We will be in a much better place, hopefully. So to round this discussion, in terms of learnings, in terms of the things that we discussed at the beginning. Artificial intelligence in general, if we can bridge the gap and AI really helps us to democratize access to knowledge, and AI understands us better, and we have the human in the loop, I think this is the promise that AI, that we have been waiting for. If AI is not democratized, if AI does not really understand us and is only allowed to be owned by a few, then we will be in the same or worse situations that humanity has been in before. So I close my talk here. I will be very happy to hear any questions or comments you might have. And yeah, so thank you very much. Thank you.
And anybody, do you have any question?
And we agreed that questions can be in Spanish, so por favor, siéntense libres de hacer preguntas en español. No hay problema. Aquí tenemos inglés, español, lo que usted guste. Muy bien.
Bueno, me hizo recordar la
sí, con el micrófono, porque ni siquiera yo lo escucho, perdón.
Bueno, Juan Villegas de Ciudad de México. Juan. Me hizo recordar la última investigación que estaba trabajando el doctor Olague, el focus of attention. Entonces, mi pregunta es si usted, para construir el patrón de qué es lo interesante en una escena, por ejemplo, de cuánto tiempo segmenta el video. El video, por ejemplo, toma una ventana de, pensemos, 3 segundos. Sobre esos 3 segundos a 30 cuadros o 20 cuadros, frames per second, busco los puntos de interés y un cluster de estos puntos de interés, cómo detectar en un entrenamiento, porque a mí se me ocurre, por ejemplo, los videos de entrenamiento de la dificultad de las tareas. Cuando una tarea es compleja, ¿cuántos puntos detecto? A mí se me ocurriría trabajarlo con programación genética, por algo que hice en mi doctorado, pero no sé usted en su trabajo si el focus and diversification, esa parte, el patrón lo construye de forma evolutiva o ha trabajado en ello. Me interesaría mucho. Bueno, gracias. Excelente plática.
Sí, gracias. Quiero estar seguro de que entiendo en qué área nos enfocamos. ¿Estamos hablando de los sensores procesador o de...?
Sería en understand.
En el entendimiento de...
En video, porque
sí.
En una imagen, pues obviamente nada más tenemos puntos de interés y puedo describir lo que hay en ella. Pero me llamó la atención esto que usted pone como que sucede algo interesante.
Sí.
Cuando, por ejemplo, puede estar manipulando algo, pero en cuanto comienza
ya entendí. Sí. Eso es algo, sí, esto ya entendí, gracias.
Y el struggle.
Y el struggle, sí. Son ligeramente diferentes. Sí. La primera es cómo detectar atención. Cómo detectar que una persona está teniendo atención. En el sistema que desarrollamos Glacier, lo que tenemos en el Google Glass, tenemos un sensor inercial que detecta cuando la cabeza, detecta la velocidad angular de la cabeza. Y cuando detectamos que la velocidad angular de la cabeza está dentro de un rango, sabemos que la persona está enfocada en un punto, y eso funciona cuando uno está interactuando con las manos. Hubiéramos podido usar un sensor de vista, un gaze sensor, pero el Google Glass no tenía gaze sensor, entonces inventamos esto de detección de atención con sensores inerciales. Y cuando detectamos eso, el sistema empieza a capturar video, que después puede editarse, pero empieza a capturar ahí y deja de capturar cuando la atención se mueve a otro lugar. ¿Sí? Eso está en el artículo de Glacier que publicamos en Augmented Human, pero te puedo dar una referencia. La siguiente parte de la pregunta es el struggle, que es ¿cómo reconocer el struggle? O la pregunta, ¿cuál es la...? ¿Sí?
Sí, ¿cómo reconocer eso? Lo que hace un niño, ¿no? El video
Ah, sí,
Para nosotros es un ser humano,
sí,
ser inteligente,
sí,
pero en asistencia, otro modo, por ejemplo, como de en ese mundo hay un problema que está pasando ahí que interrumpe
sí,
la tarea, cómo asistir. Un ejemplo que se me viene clásico, ¿no? Todos cuando desarmamos una computadora, la
sí,
técnica clásica o un aparato, a mí me enseñaron
sí,
por separado,
sí,
tornillo que
los
quitas,
tornillos.
ponlo en la misma
Así aprendí yo
posición,
también, sí,
acá, cuando la tapa,
sí,
para cuando tú vuelves a
sí,
armar,
sí,
sepas la posición del tornillo que quitas.
sí, sí.
Pero eso es, por ejemplo, para nosotros. ¿Cómo hacer? Aquí sería un scroll, o algo así. Igual me dio una idea para poder trabajar en esto con una tesis, con un proyecto. Pero, ¿cómo hacerle? ¿Cómo evolucionar un patrón? A mí lo que se me ocurre es, a partir de los atractores inerciales, esto, en el video, extraer algún rastro, viajes, para eso que hay ahí, ¿qué hay? ¿Dónde no? Pero, bueno.
Sí, es un área que para mí también es muy fascinante y muy temprana. Hay mucho por desarrollar ahí.
Es que yo lo veo como una diferente forma de entender, porque una cosa es detectar qué hay en la imagen.
Sí.
Los agentes, los sujetos de la imagen, ¿qué están haciendo?
Así es.
Y dentro de lo que están haciendo, ¿cómo aislar el antes, el durante y el después?
Totalmente de acuerdo. Y creo que ahí es donde estos sistemas de inteligencia artificial te tienen que mover al entendimiento más de la persona. Es no la tecnología, ya tenemos tecnología muy avanzada, sistemas de posicionamiento avanzados, generación de contenido, ahí va, todavía no está perfecto, pero en el entendimiento de la persona y entendimiento de cuándo tienen que realmente ayudarnos, eso todavía falta y es por lo que motivó el desarrollo de detección de struggle. Sí. No, gracias y feliz de platicar luego más. Aquí hay otra pregunta. And by the way, anyone that wants to ask in English, for sure, okay? So that any feel free. Sí.
Just a kind of suggestion. This is because I have a T-shirt that I wear very proudly. This is a cartoon. You remember for sure the Roadrunner.
The who?
The Roadrunner.
Ah, yes, for sure, yes.
And my T-shirt says the King of Struggles. And probably you can try to
Yes.
to.
It's a good idea. So yes.
Because technically, theoretically, the devices made by the Coyote, they were perfect.
Right.
Try to find out
Yes.
this kind of system.
It's a good analogy. I agree.
Yeah, sure. I am sure that you will learn a lot.
When you were talking about that, I also felt that you could use those old cartoons from the Roadrunner, Tom and Jerry. Tom and Jerry struggles a lot, right? So any device that we build that is able to recognize struggling humans should be able to recognize struggling cartoons or struggling animals, right? Which it will be extremely exciting to have that universal ability of recognizing struggles.
Not to consume too much time, it comes to my mind one kind of anecdote when I was talking with my cousin, nephews, toddlers.
Yes.
They try to make their parents to buy the Batman or Superman tennis shoes, and they put in the corner, in the ceiling. They were about jumping, saying, "Hey, my tennis shoes doesn't fly." Just to try to get some safety or to avoid something.
Yes. Yeah.
That is some kind of suggestions.
Yeah. Thank you very much. Thank you. Por allá, tenemos una ahí. Gracias.
Primero agradecer por la plática, muy interesante, y me dejó pensando esta parte de entender lo que estamos, de entender las acciones que estamos realizando, ¿no? Y me puso a pensar, bueno, actualmente con estos sistemas generativos de información que aprenden de cantidades enormes de datos que tenemos disponibles, se pudiera usar, por ejemplo, todo este banco de tutoriales que tenemos en Internet para, de cierta manera, primero clasificarlos acorde a tareas, acciones, y de ahí partir para, pues, generar, ahora sí que, una vez que detectemos cuando está alguien lidiando con un problema, utilizar ese banco de información para generar incluso correcciones, ¿cómo se podría decir? Pues ayuda al usuario que está realizando una tarea. Es posible esta cuestión, pero primero habría que establecer métricas que evalúen las acciones, ¿no? Eso yo creo que es como que el momento ahorita, según entendí, no sé si sea correcto. Y después de esas métricas, llevarlas a evaluar después la acción que está realizándose, ¿no? Tengo entendido. Entonces mi pregunta sería, si el trabajo se guiaría ahí a establecer una evaluación para estas acciones y elegir cuál es la acción adecuada de nuestro lado para apoyar esa acción, ¿no? Ese es mi idea, sería establecer estas métricas de evaluación.
Sí, es un punto importante. Mi preferencia, pero esto tiene que demostrarse si es correcto, sería que no tuviéramos que establecer métricas específicas, sino una métrica genérica que nos permita entender que la gente está teniendo dificultades. Porque si logramos hacer eso, si logramos, bajo tu punto, etiquetar toda la información que está ahí afuera en el mundo, o al menos una fracción que nos permita tener diversidad suficiente para poder reconocer que la gente o quien está ahí está teniendo dificultades, entonces no necesitas más que esa métrica, más que la métrica de esta persona está teniendo dificultades ahorita, o este robot, o este dibujo animado. Si logramos hacer eso, creo que ese sería como la estrella del norte que se dice en inglés, ¿no? La North Star. Eso sería lo ideal, porque significa de que tienes ya entonces un sistema universal que puede clasificar toda la información que está afuera. Pero posiblemente al principio, así como lo hemos hecho nosotros, tenemos que ir como que paso por paso, caso por caso, tratando de entender hasta que podamos tener o más datos o algo más revolucionario que nos permita entender qué es lo que nos está faltando para reconocer universalmente el reconocimiento de la dificultad.
Gracias.
Sí, gracias. Aquí. Aquí, a ver, David.
Hello, I'm David Demichi. It's a pleasure. So, you talk about AI that understands us better. So, my question is, what is something that human being still doesn't understand very well that AI that does understand and can help us to recognize ourselves and can help us in the future? What do you think is that part that we don't know about us and what AI knows about us? So can you tell me that, please?
That's an excellent question, David. Thank you for asking. And I don't have the answer to that in general. I mean, there are some things. There used to be something called the Moravec paradox in robotics. And Moravec observed that humans are really good at doing some things that robots are really bad at. And then robots are really good at doing some other things like moving really fast.
Tenemos un break de unos 10 minutitos. Si quieren pasar, por favor, a la parte del fondo donde está, iba a decir las cervezas, pero el agua, las ollitas, y por favor en 10 minutos continuamos con la sesión.